Going live. Check. All right. Come on. All right, we're going live. See if anyone shows up. Hopefully, we'll see. All right, we'll just record the lesson. Hello. Okay, so please post in the chat if you can, if you have questions. But today is really not just a Q&A session. It's going to be just me going over a lesson with y'all. There might be some natural pauses in there where you can ask questions. If you can't ask in the chat, email me. But email me at the fcps.edu, not the schools.net email. fcps.edu is the one I'll be monitoring as we're going. I know there's a delay, so it's a little awkward, but that's what we're going to be doing. I want to wait until 10:30 to officially start, but here we go. Okay, but in the meantime, while we're waiting, if you know you have any questions, you feel free to post them in the chat, or send an email. Okay. All right, it's 10:30. We're going to go ahead and roll. Okay, so here's the deal, guys. We're getting a lot of mixed messages from the county, from our administration of what's going on. So this is the deal. This is how I foresee it. So on Tuesdays, I am going. Well, it's up to you, Aaron. It's up to you if you want to take notes. You might want to just listen this time around, and I'll post a link to the video so you can go back and replay it if you want to. I'm going to be going over that outline I just emailed you a couple earlier this morning. That's what I'm going to be doing first, and then I'll be doing some of the stuff from the solution stoichiometry PowerPoint. But so it's really up to you if you want to take notes or you just want to watch. Okay. So here's the deal. I'm going to be doing a lesson or two a week. And they'll be probably through YouTube, unless we get confirmation that Blackboard Collaborate Ultra is working better. They'll probably be through YouTube. I'll tell you the time that I'll go live, so if you want to watch it live, you can. But I will also post the link, so if you can't make it at that time, maybe you're meeting with another teacher or something, that's fine. You can just watch it another time, okay? We're still going to have office hours, and we're going to still use YouTube Collaborate Ultra for those office hours until we can't anymore. So tomorrow, remember, I have office hours from 12 to 1:30 and 3 to 4. If you have questions, feel free to come during those, okay? We will be going through the Blackboard Ultra, which means you will have to go, or Collaborate Ultra. You have to go to the AP Chemistry Blackboard room and go into the Collaborate Ultra button to find the office hours. But that's where I'll be to start. But if enough kids are saying, hey, I'm trying to get in and it's not working, then we might end up coming back to YouTube for our live office hours, okay, on Wednesday and Friday, okay? So just a couple notes. For those of you in sixth period, we really haven't had an official class, and we probably won't until I have no idea how it's going to happen. So what I'll try to do is I'll try to do one of my lesson tapings. I'll do it during normal sixth period on Thursday this week, so you guys have a chance of being there. But I don't know what other teachers are doing, if they're doing synchronized lessons or if they're doing asynchronized. We're getting mixed messages from the county. So some people might be free to come meet me right now during 10:30 that wouldn't have been last week. Okay. So we're just going to see how it goes doing it this way. So I'm going to post the lesson. You have all the practice. You can work on the practice. You can come talk to me during office hours and ask questions. And you can always email me your questions. And then, we'll move from there. So a couple big announcements. That Unit 6 or optional test that was going to be given to you this Friday, you're going to have the opportunity. It's been pushed all the way until next Friday. Again, it's because of what happened to Blue Day classes. So to make it fair for those students, we're pushing it another week. So that optional Unit 6 test will be next Friday, May 1st from 3 to 5 p.m. Okay? So that, and I will also, in the next couple days, I'll post a checklist for that test. So you have the review material, so hopefully you've been doing that. The test review, and you should come in during office hours to ask questions about that. But I will also post a checklist for you to help you study as we approach next Friday. Again, it's been moved to May 1st, okay? But now we're going to get into a new lesson, Molarity. Those of you that were with me beforehand on YouTube before spring break, we've kind of covered this already. But I want to go through it a little bit more in detail, and we want to get into solution stoichiometry. Now, this stuff won't be on the Unit 6 test. That's next Friday, but there will be another assessment on this material later on that, again, could help you get to that grade bump, okay? So let's talk about solutions. Okay, so today we're going to talk about solutions and molarity and solution stoichiometry. Okay. Okay, so again, I emailed you this outline earlier today, but if you want to, just follow along with me. Okay. So we're going to focus on solutions, but more importantly, we're going to focus on aqueous solutions. Okay. So what does that mean? It means water is going to be the solvent. So there's all different types of solutions, like air. The air we breathe is a solution. It's a mixture of different gases. Okay, all solution means is a homogeneous mixture. That's all that means. Okay, but we're really going to focus on things dissolved in water, right? A lot of times you hear the saying that water is the universal solvent. It's because a lot of things mix well with water. Okay, and that's what dissolved means. That's what aqueous system means. It means the things mix well. They mix so well that you can't look at them and distinguish one part from the other part. Okay, that's what a solution is, a homogeneous solution. You can't look at the mixture and tell what is the salt and what is the water. They look the same. Okay, so we're going to just focus on aqueous solutions. Okay, so the first thing I want to talk about are the two types of aqueous solutions you can have. And there's electrolyte solutions and there's non-electrolyte solutions. Now, real quick, all electrolyte means is that it's something that when you add it to water, the resulting solution can conduct electricity. Okay, that's what electrolyte means. Okay, so an electrolyte solution is a solution that can conduct electricity. A non-electrolyte solution is a solution that can't conduct electricity. Okay, well, there's certain things that you dissolve in water that cause it to conduct electricity, and there's certain things that you dissolve in water that don't allow it to conduct electricity. So the definition is really anything that when it mixes with water produces charged particles, produces ions, cations, anions, whatever. It has to be a charged particle. If you produce ions when you dissolve in water, when you mix with water, when you make a solution with water, you are considered an electrolyte. Okay? Well, the two types of compounds that commonly do this are salts, ionic compounds, okay, and acids. Remember, anything with that H in front. Now, there's also the organic acids, and they are also electrolytes, like vinegar and stuff like that. But remember, vinegar is also acetic acid. It's the same thing, okay? So acids, whether they be organic or just inorganic acids, just have an H in front. That's what we're thinking, H with an anion, are considered electrolytes, and same with ionic compounds. Okay, so what does that mean? It means other things that mix with water that aren't these things, salts or acids, they're going to be non-electrolytes. Okay, so what happens when a salt dissolves in water? Well, let's just use sodium chloride as an example. What does aqueous mean? It means in solution with water, but what does it really mean? It means your particles, the particles of the compound, the solute that is dissolving in the solvent, which is water, have separated. Well, the particles of an ionic compound are the ions themselves. Okay, so ionic compounds will separate and be surrounded by the ions will separate and be surrounded by water molecules, and you'll get sodium by itself and you'll get chloride by itself. Okay, well, notice that now I have ions in solution, so I'm an electrolyte. If I have charged particles in solution, I can conduct electricity. Okay, acids do the same thing, but notice the difference. Look at HCl here. It's HCl aqueous yields H plus aqueous, Cl minus aqueous. Here it's sodium chloride solid yields sodium ions aqueous, chloride ions aqueous. Okay, so HCl will mix with water and it will mix with water, but the question is, does it break apart into H plus and Cl minus or does it stay together? Okay, well, HCl does break apart into H plus and Cl minus when you add it to water. And so because it produces charged particles, it is an electrolyte. Now, why do we call it an acid? For our purposes right now, we can say anything that produces H plus in water is an acid. Now, the definition gets a little bit more complicated later on, but we're not going to get into that, unfortunately, this year. Okay, so right now it's just it produced ions. Do I have ions in solution? Yes, it's an electrolyte. Okay, now we want to visualize this a little bit better, right? So here's kind of the representation right here of salt as a solid, and then this would be aqueous salt, right? So we'll say, sodium, the sodium ion is the positive one, the negative one is chloride. That's the solid sodium chloride. But what does it mean to be aqueous? It means water molecules come in here. And remember, we know the hydrogen sides of the water molecules are positive. The oxygen sides of the water molecules are negatively charged because of the polarity of the water molecule, right? And the water molecules are going to orient themselves so that opposites attract, right? So the hydrogens from the water are going to be attracted to the chloride. The oxygens from the water are going to be attracted to the sodium. And that's how they're going to orient themselves. All right, so the ions have separated. The ions are separate from each other, but they're surrounded by water molecules. That's really what aqueous means. This picture is a pictured representation of this exact equation right here. That equation and this picture are representing the same thing. Okay, but that's what it means for an ionic compound to be aqueous. It doesn't mean it's here. This is an ionic compound solid. This is an ionic compound aqueous, right? Okay. And we could do the same thing. So again, we could show a little bit more detail. Notice I got the partial negative sign because we're talking about a polar molecule versus the full positive sign of a positive ion, right? And notice we have these interactions, okay? And we can name those interactions. We know how to name these interactions, right? I could just call this, right? So what do we call the interaction between the hydrogen side of a water molecule to the oxygen side of a water molecule, right? We call that a hydrogen bond. And a hydrogen bond is just a special part of a dipole. Well, remember, we call that partial negative, we call that the negative dipole. We call that partial positive the positive dipole. So that's a dipole and that's a dipole. All right. Well, what do we call this blue positive thing? What do we call this green positive thing? We call those ions. So guess what we call this interaction? We call it an ion dipole interaction. That's an ion dipole interactions. Okay. So and we can get more complicated with it. We don't need to get that complicated with it. But what needs to happen for an ionic compound to actually dissolve in water? Well, the ions have to separate. The positive and negative ions have to separate. That requires energy, right? Positive and negative ions are attracted to each other. So to pull them apart away from each other requires energy. It's like pulling magnets apart that are attracted to each other, right? Well, water molecules are attracted to each other too, right? You got hydrogen bonding between water molecules, and they have to separate to make space for the ions. Okay, well, that requires energy. But then new forces of attraction are formed. And what are those new forces of attractions? They're the ion dipole interactions. Those new forces of attraction form, and when force of attractions are created, that releases energy. So you have these different processes. Two of them are endothermic, requiring energy. The water molecules have to separate from each other to make room for the ions. The ions have to separate from each other. That requires energy. But then when the ion dipole interactions are formed, that releases energy. So whether or not the overall process of dissolving a salt in water is going to be endothermic or exothermic really depends on the sum of those three steps. Two of those steps are absorbing energy. One of those steps is releasing energy, and it really just depends on how much energy is released versus how much energy is absorbed. All right, but that's kind of getting down the road. What we really want to understand is this is a particulate diagram representation of aqueous sodium chloride. Right, this right here, just right there, that positive ion with those three water molecules is the particulate representation of this. You can see that. Okay. That picture right there is the same thing as that. That and that are the same thing. And we want to be able to put those two things kind of together. I want to be able to see this because that's the way it's going to be written, like on a test or something. That's how we're going to express it. But I really want to understand what that represents, and it really represents that. That notation represents this is what's really going on the molecular level. Okay? All right. So we keep going. All right. Now this shows aqueous HCl, right? This would be HCl aqueous because it's surrounded by water. And then this is aqueous HCl dissociated. So notice the difference. Remember, this equation was solid to aqueous ions. This is aqueous molecule to aqueous ions. Aqueous molecule to aqueous ions. So that's showing the HCl dissolving in water. Okay, so again, this is just a particulate diagram showing that. Okay, all right. So let me just pause there for a second. See, okay. All right, again, if questions pop up, feel free to put them in the chat or send an email as I go through. And every once in a while, I'll stop and I'll check the chat for questions, okay? But let's just keep going then. Okay, so yeah, there is such thing as strong versus weak electrolytes. Strong electrolytes give you a lot of ions in solution. Weak electrolytes give you only a small amount of ions in solution. What's the difference? Well, if you did a conductivity test, the stronger the electrolyte, the more conductive it is. The weaker the electrolyte, the least conductive it is. Okay? So, what do you need to know about strong versus weak electrolytes? Well, we can get into the weeds here. It's not really that important at this level of chemistry, but strong electrolytes are things like salts and what we call strong acids. Weak electrolytes are weak acids. Well, what's the difference between a strong acid and a weak acid? Okay, well, let's go through that definition. Okay, I'm going to explain the definition. I'll show you a particulate diagram and we'll try to understand. Okay, HCl is a strong acid. Now, the definition of a strong acid is one that completely ionizes. It's an acid that completely dissociates when added to water. Okay, what does that mean? It means if I put 100 HCl molecules in water, I'm going to end up with 100 H pluses and 100 Cl minuses. I'm going to end up with 0 HCl's still together. So if we go back to that reaction, all of this will turn into that. That's what we're saying. That's the definition of a strong acid. Okay. And a strong acid is a strong electrolyte. So HCl is a strong electrolyte. Okay. Well, what about a weak acid? A weak acid is a weak electrolyte. Well, what does that mean? It means you're not getting as many ions. Well, if you look at HF and HCl, for every one molecule of HF, there's 2 ions. There's H plus and F minus. And for every one molecule of HCl, there's 2 ions, 1 H plus and 1 Cl minus. So the question is, why is HF a weak acid and HCl a strong acid? Well, this is the difference. for every 100 HFs I put in water, only one of them or so will disassociate and the rest will stay together. So 99 of them will stay as HF and I'll only get one H plus and one F minus. So for the same amount of HFs I have in solution, I get a lot less ions. And the less ions you have in solution, the less conductive your solution is. Okay? And so some acids completely dissociate, and if they do, by definition, they're strong. And some acids only somewhat dissociate. And if they do, they're defined as a weak acid. The weaker the acid, the less it dissociates. Okay? This isn't, these aren't actual numbers. I'm just kind of giving you an example here. It's not 100, one out of every 100 molecules of HF will dissociate. That's not what I'm saying. I'm trying to give you an example of what it would mean versus be strong versus weak. Okay? Okay. So let's keep going here. Okay. But okay, so here's kind of the particulate diagram of strong versus weak. So strong acid, you start out with all of it together, but after it's added to water, all of the ions separate. Notice they're not together anymore, right? And notice you don't have any HA left over. But if you look at this, weak acids, a couple of them broke apart so that you get a little H plus and a little B minus, but notice the majority of your solution is still just HB together. Okay? That's the difference between strong electrolytes. I got a lot more ions in solution. Remember, these molecules right here aren't ions. So if I just had those molecules right here in this picture, my solution would not conduct electricity. Okay? But this solution will because I do have a couple ions. Okay? So this solution is going to conduct electricity, but not as much as this solution because this solution is nothing but ions and it's going to be very conductive. Okay? All right. Oops. Okay. So let's keep going here. Whoops. All right. So then what's a non-electrolyte? Okay, non-electrolytes are things like sugars and alcohols. Okay, so like if you went back to our IRP, and remember we're going to be doing an IRP lesson in a couple weeks. One of your solutions was basically sugar water, and if you were researching what you were going to do, you would probably figure out, okay, sugar water does not conduct electricity, where the rest and the alcohols don't conduct electricity, but the rest of your solutions do conduct electricity. Okay, so when sugar dissolves in water, it's not like sodium chloride breaking up into smaller ions, okay, charged particles. All it happens is each molecule of sugar just gets surrounded by water. So in sugar as a solid, it's just molecules surrounded by molecules of this identical molecules surrounded by identical molecules, right? Aqueous is just those individual molecules are now surrounded by water, but notice they're not charged, okay? So this is kind of the representation of that. So here is glucose by itself, right? In the solid state, and just imagine just repeating units of this stacked up on each other, and that would be the solid structure of glucose, okay? Versus glucose aqueous, just surrounded by water molecules, okay? So yeah, the particles separate, but the particles of a molecular compound are just the individual molecules. It's not ions like in an ionic compound, okay? So I don't get charged particles, so when sugar dissolves in water, yeah, it mixes well with water. I could look at a solution of salt water and a solution of sugar water, and they look exactly the same, right? And the process of them looking exactly the same. I could pour some sugar into water and watch it dissolve, and I could pour some sodium chloride into water and watch it dissolve, and it would all look the same to me. But then if I tested their conductivity, the salt water would conduct electricity and the sugar water wouldn't. Why? Because the salt water has ions that are moving around, and the sugar water doesn't have any ions in the solution that are moving around. Okay? All right. So again, this is kind of what the test would have looked like for your IRP. Any electrolyte would light up the light bulb. This is the difference between a strong electrolyte and a weak electrolyte. But the sugar you would have conducted would not have lit up the light bulb. Okay. All right. Okay, so that's kind of like we want to have an idea of those particle diagrams, what it really means to be an aqueous ionic compound versus like an aqueous, you know, molecular compound like glucose or something like that. Ions versus just molecules mixing with water. Okay. But now we're going to get into kind of the math we're going to be doing with solutions. And the first part of that is our measurement of concentration. Okay. So concentration is, it's how concentrated your solution is, right? So, you know, if you have very concentrated, like if you ever made Kool-Aid, like if you ever bought Kool-Aid, like in the big jumbo pack, you have the powder. Some people like to make their Kool-Aid very concentrated. That means they're putting a lot of it in, a lot of that, scooping a lot of that sugar in there. And some people like it a little bit more dilute, right? It really depends, right? Concentration is a measurement of how much solute, how much stuff are you dissolving, how much salt have you dissolved in the water, how much sugar have you dissolved in the water, how much acid is in the water, right? It's how much stuff is in a given amount of either solution or solvent. And solvent is just going to be water in this case, okay? But our measurement, so you can measure concentration however you want. You could do grams per milliliter, right? It's a density, but uh, it could also be a concentration. It could be this many grams of salt per milliliter, right? This many grams of sugar per liter, right? That grams per liter would be fine for a measurement of concentration. But our measurement of concentration, the one that we use all the time, is what we call molarity. Okay? And what is molarity? Molarity is moles of solute per liter of solution. That's what molarity is. So how do you calculate molarity? You take the moles of solute you have, you take the volume of your solution in liters, it's got to be in liters, moles divided by liters, and that's how you get molarity. Okay? So like it's moles of the solute. So like if we're talking about a sodium chloride solution in water, right? It would be moles of sodium chloride per liter of the entire solution. Okay. If HCl was my solute, then it would be moles of HCl for every 1 liter, right? Okay. So simplify it. Molarity is moles over liters. Simplify it anymore. Notice capital M, okay, is our symbol for molarity. So when you see that capital M, that's a measurement for molarity. I think it's a lot better for you to think, anytime you see capital M, think of it as moles per liter. I think that's a better way to think about it, just like thinking about density as grams per liter or something like that. So instead of saying density is capital D or whatever, say density is grams per liter or grams per milliliter or whatever, grams per gallon or whatever. Okay. So instead of saying capital M, say moles per liter, because that gives you a better idea of what that measurement's all about. All right. Okay. All right. So, and the way to say that, like the way to read this, is to say I have a 1.50 molar solution of sodium chloride. Capital M, the way to read it is use the word molar. So molar means capital M. Okay. So let's say we're given this. That means I have a sodium chloride solution. So sodium chloride is my solute. And the molarity, the concentration is 1.5 molar. The molarity is 1.5. What does that really mean? Remember, that means moles per liter. So what we're saying is, what this measurement means here is every 1 liter of this solution, there'll be 1.5 moles of sodium chloride. So if I pour out a liter of that solution, I know I'm going to be pouring out 1.5 moles of sodium chloride. Now, the way to really interpret it is two conversion factors. And now we can start doing some dimensional analysis. We can start doing some stoichiometry. So given this, you have this. You could say 1.5 moles of sodium chloride over 1 liter, or you could say 1 liter for every 1.5 moles. I could use this conversion factor here to cancel out liters and get moles. I could use this conversion factor right here to cancel out moles and get liters. And that's really how we're going to be using our measurement of molarity. We're going to be using doing dimensional analysis with it. Okay. Now, that's not the only way to interpret this. Let's keep going. Let's go back to what we started with, right? When you see sodium chloride aqueous, remember, that doesn't mean sodium and chlorides are together. It means sodium and chloride is separated. Sodium surrounded by water, chloride surrounded by water. They're separated now. All right. Well, if you see that, if we go back to that measurement, another way to think about it is instead of saying 1.5 moles of sodium chloride, you could just say 1.5 moles of sodium ions for every 1 liter, or 1 liter for every 1.5 moles of sodium ions, right? Because that's really separated, okay? And you could say the same thing about the chloride ions. But the reason why that number hasn't changed, it's 1.5 for the sodium chloride, it's 1.5 molar for the sodium chloride, but it's also 1.5 molar for the sodium ions, and it's 1.5 molar for the chloride ions, is because the subscripts in my formula for sodium chloride, my subscripts for sodium and chloride are both 1. All right. Well, let's keep going. All right. Well, what if I have an ionic compound that has a little bit more complicated formula? Okay, let's do aluminum sulfate. So what we said, the same concentration, 1.5 molar solution of aluminum sulfate. Well, first, we really got to know, how does this ionic compound break up when it dissolves in water? And it breaks up into the ions that make up the compound. And there's 2 ions that make up the compound, aluminum ions and sulfate ions. The sulfate doesn't break up into anything smaller. It doesn't break up into sulfur and oxygen. It just, so what does it break up into? 2 aluminum ions and 3 sulfate ions. Okay? So what we're saying is, for every one of these compounds, one of these formula units, you get 2 aluminums and you get 3 sulfates. So you get a total of 5 ions. All right? So let's go back. You're told that the molarity of this compound is 1.5. But now, what do I do? What's the molarity of aluminum? Well, I get 2 aluminums for every 1 aluminum sulfate. So the molarity of aluminum is double the molarity of the compound. There's 2 aluminum ions for every one of these compounds. So the molarity of aluminum would be 3. And just real quick, just a side note, when you see something in brackets, like I have aluminum brackets, that means the molarity of aluminum. So when you start to see brackets in equations for chemistry, brackets means molarity. So brackets aluminum 3 plus means the molarity of aluminum 3 plus equals 3. That's what we're saying. Okay. So all I was told is that I had a solution 1.50 molar aluminum sulfate. Right? That's all I was told. Right? So this is all you're given. But these are the different ways you need to be able to interpret that. So that's all I'm given right there. Okay. Well, that means my molarity of aluminum is 3. My molarity of sulfate is 4.5. Where do we get that? 1.5 times 3, the subscript for sulfate. And the molarity of all the ions combined would be 1.5 times 5. Where do we get that? Well, again, for every one of these that dissolves, you get 2 aluminum ions, you get 3 sulfate ions, you get a total of 5 ions. Okay? So just given this measurement here, you know that, you know that, you know that. Okay? So now you know all of these conversion factors. Okay? So I'm going to do this. I'm not going to save these as is, so, okay. Right? So just given this measurement here, you can come up with all of those conversion factors. All of those. Okay? And you can include just ions too. All right? All of those conversion factors just from that measurement. Okay? Because you understand how salts ionize in solution, how they dissociate, what the particulate diagrams look like. It's 2 aluminum ions separated, 3 sulfate ions separated, all surrounded by water. Every time one unit of that ionic compound dissolves. Okay. All right. So now we're going to go to, let me just check the chat, see any questions as we're going here. Okay, no. All right. So now let's go to solution stoichiometry. All right. So now we have that new measurement, molarity, and you can do the practice problems with just molarity stuff. But let's talk solution stoich. All right. So solution stoich is no different than gas stoich. It's no different than reaction stoich. It's no different than composition stoich. It's the same thing. Okay. It's just now we really got to have to focus on, it's really what the new focus is going to be on steps 2 and 4. Okay. Take what you're given and convert it to moles. Remember, we're used to steps 2 and 4 just using our mole map, right? We could go from, if we were at volume of a gas at STP, we could use our mole map to go to moles, right? Or step 4, we could go from moles to our desired units using the mole map, okay? But what happened when we got to gas laws and we did the ideal gas law when we're not at STP? Well, I can't use my mole map. I got to use the ideal gas law, okay? Well, now, what if I'm not given grams? What if I'm not given volume of a gas at STP? What if I'm not given particles? What if I'm given volume of a solution and the molarity of solution? Okay. Well, then step 2 is going to be take what I'm given, volume and molarity, and convert it to moles. Well, let's all start a mantra right now. Okay. This is your mantra. Repeat this like 50 times, meditate on it. Liters times molarity equals moles. Just repeat that a million times. Okay. Liters times molarity equals moles. Liters times molarity, and we'll write it. Liters times molarity equals moles. Liters times molarity equals moles. Liters times molarity equals moles. Right? We're going back to our molarity equation here, and we're just solving for moles. Okay, how would we solve for moles? We would cross multiply. Molarity times liters equals moles. Liters times molarity equals moles. Liters times molarity equals moles. Say it a million times. Get it stuck in your head. Not milliliters, liters. Liters times molarity equals moles. All right? Okay. Okay. And then moles divided by molarity equals liters. Moles divided by molarity. So step 2 in solution stoichiometry, what are you going to do? Liters times molarity. Step 4, what are you going to do in solution stoichiometry? You might do moles divided by molarity. So step 2 is liters times molarity equals moles. Step 4 is moles divided by molarity equals liters. That's really all it is, but it's still the same steps. Okay? So let's do this practice problem. What mass of lead 2 chloride will precipitate if 15 milliliters of a 1.5 molar solution of lead nitrate is added to excess sodium chloride? Okay, we know it's stoichiometry. How do we know it's stoichiometry? We're given the amount of one thing. We're asked to find the amount of something else. Okay, what are we given? We're given the volume and the molarity of our solution, and we're asked to find how much precipitate will occur. All right, so we follow our steps for stoich. All right. Okay. So what's step 1? Write our balanced equation. So we got lead nitrate plus sodium chloride yields lead chloride plus sodium nitrate. Okay, it's double replacement reaction. We would use our solubility rules to figure out that lead chloride is the precipitate. I think the question told us what the precipitate was, but if they didn't, we'd have to be given our solubility rules. Okay, it told us what the precipitate was because it said what mass of lead 2 chloride will precipitate. So it told us that, but if it didn't tell us that, if it just said what mass precipitate, we'd have to identify the precipitate. We'd have to use our solubility rules. But in this case, they told us the precipitate. Okay, great. So what's step 2? Take what we're given and convert it to moles. What we were given volume and molarity. Okay, so how do we take volume and molarity and convert it to moles? Liters times molarity equals moles. Liters times molarity equals moles. Well, they didn't give me liters. They gave me 15 milliliters. So you just need to be able to do this. Right? Yeah, you divide by 1,000, but you just move the decimal place to the left 3 times. All right. If you want to move further on in your chemistry career later on, college, wherever, you just need to do that conversion in your head. Okay. Don't waste your time writing the 1/1,000. Okay. All right. Anyway, let's go back. All right. So that's this step right here. Liters times molarity gives me moles, right? This is how we interpret that measurement. 1.5 molar solution of lead nitrate, we say 1.5 moles of this over 1 liter. Or we could say 1 liter over 1.5 moles. But in this case, we want to cancel out liters and get moles. So that's that part here. So this is step 2 right here. Liters times molarity gives me moles. Okay, step 3 is the stoichiometric step. It's a 1-to-1 ratio. 1 mole of this, so we convert to moles of lead chloride. And now we can go back to our mole map because we were asked for mass. Moles to grams, this right here, 278.1, is the molar mass of lead chloride. Okay, and we get our answer, 6.3 grams of lead chloride. Okay, so what solution stoichiometry all about? It's just understanding this measurement of molarity. That's all it is. Understanding this measurement of molarity. Okay, this right here is a molarity. 1.5 moles per liter. Moles per liter is molarity. Okay, right there. So that's it. That's the only thing that's new. Okay, this is stoichiometry. This is balancing. This is stoichiometry. The only thing that is new is just another conversion. Another conversion we have to know about. How do we get from this measurement to moles? How do we get from this measurement to moles? How do we get from grams to moles? Divide by the molar mass. How do we get from liters of a gas at STP to moles? We divide by 22.4. How do we get from particles to moles? We divide by Avogadro's number. Now, how do we get from liters in molarity to moles? Liters times molarity equals moles, right? That's it, okay? All right, that's all we're getting at there, okay? So let's come back to these, our notes here, okay? And again, I'm kind of going through this fast. I want you to practice and I want you to come to office hours and ask me questions, okay? We're going to do more with solutions and what we call net ionic equations next week, but this is really the most important part of it is the molarity part, okay? Now, another equation you want to know that includes molarity is the dilution equation. So let's understand what dilution is, right? Dilution is just how do you dilute something? Well, a lot of people would just say you add water. Well, that's the key. That's usually the case because water is the universal solvent. So how do you dilute something? You add more solvent. And so again, for our purposes, that means you add water, right? If my Kool-Aid's too sweet, add water. My Gatorade's too sweet, add water, right? Right? This is kind of a crude example, but like if you have a dog and it pees on the grass and the grass is not growing, every time the dog pees, you should spray the area where he peed with water. Why? You should dilute it. Dilution is your solution. Okay? So anyway, all dilution means is add water. Okay? So, but what does it do? It decreases the concentration, right? It decreases the concentration. If you go back up to this equation, right? Our molarity equation, right? If you add water, you're increasing the volume of the solution, but the moles of solute are staying the same. You're not adding more salt, you're just adding more water. So the volume increases, the amount of solute stays the same. So the numerator stays the same, the denominator gets bigger. What happens to the molarity? It goes down, right? So it gets less concentrated. Molarity is our measurement of concentrated. The higher the molarity, the higher the concentration. The lower the molarity, the lower the concentration. Right? So dilution is just the process of lowering the concentration. How? By adding more solvent. Okay? In our case, adding more water. Right? This is the dilution equation. All it says is M1 times V1 equals M2 times V2. So the initial molarity times the initial volume equals the final molarity times the final volume. You might recognize this. It might look a lot like Boyle's law. P1 times V1 equals P2 times V2. Notice that This is an inverse relationship, just like Boyle's law shows an inverse relationship between pressure and volume, right? As molarity decreases, volume increases. It's usually as volume increases, molarity decreases. Okay, so that's just an equation to think about when you're doing some of this molarity practice problems. Okay, all right. So that's really kind of ends it today for the lesson. I want to stay here. There's a few people here. If you have questions, please email me. Um, please email me and uh, or post in the live chat. Okay. Um, all right. And if there are no questions, again, I'm going to post this video on Blackboard and I'll send out an email to the link if you want to watch it again. And for all the people that couldn't make it during the live chat, they can watch it on their own. I plan on having office hours tomorrow. We're going to try the Blackboard Collaborate Ultra. So remember, that's through the AP Chemistry class in Blackboard. Go there. We'll try office hours. If for some reason you're trying and you can't make it through there, it's not working for you, email me. And in live time, as we're if I get emails from students saying they can't get in there for office hours, then I'll come back out of there and we'll get back on YouTube and do the office hours there. Okay. I like the collaborate for office hours because there's not a delay and we can kind of just go back and forth kind of quickly. But I kind of like the YouTube for doing these videos, and I don't have to do them live, but I just kind of like to answer questions on the fly. But because I feel like I can show the screen a little bit better. I feel like there's a little bit more freedom here with how the screen looks compared to the Collaborate Ultra sessions. I think for viewing it after the fact, I think it's a little bit easier doing it on YouTube. But what I'm planning on doing is over the next couple days, we're going to dip our toe back into Blackboard Collaborate on Blackboard and see how it works. And if it works, then maybe that's where I'll do the rest of our lessons. But right now, what I plan on doing is, we'll do 1 or 2 lessons a week. I'll announce when I'm doing those lessons on YouTube. If you can make it live, great. And if you can't make it, then you can watch it on your own, and then just come during office hours to ask questions. And I think that's kind of how the plan's going to be based on what we're getting from the county. It's really kind of frustrating getting one message from one person and another message from another person on what we can do, what we can't do, that kind of thing. So it hasn't really been an issue going on YouTube. It's been working. So let's just use that for now for our live lessons. But for office hours tomorrow, I do want to test the Blackboard Collaborate Ultra just to see how that works, and just to go from there. Okay. I plan on doing another lesson or at least a live Q&A session during 6 periods class on Thursday. So that would be what in 6 period? Is that like I think 12:30 to 1:15, I think, something like that. And I'll make the announcement, and it'll either be YouTube or Blackboard Collaborate Ultra. I'll make the announcement, but just because I haven't had a chance to check in with my 6 period kids like officially, like I was able to do that with 3rd period, and I was able to do that with 7th period last Tuesday, but we didn't have that chance on Thursday for 6th period, and I don't want to cheat them out of that. But if Blackboard Collaborate Ultra can't handle 100% of the high school students all coming on at the same time, then we're going to have to do this, kind of a different way. Okay. So I haven't gotten any questions in the chat or via email. So we're going to stop here. I appreciate those of you that did show up. And if and those of you that are just watching it now because you couldn't make it. Again, I'll see you office hours tomorrow, 12 to 1:30, and 3 to 4. Okay, we're going to try Blackboard Collaborate Ultra. I'll send out an email if it's not working, if I go to YouTube Live. Okay. Yeah. Okay. So all the assignments, they're on Blackboard. They're also I sent them out to you via email, so you have they're either in your email or you can get them on Blackboard. If Blackboard doesn't work, you got them in your email. If you delete the email, then they're in Blackboard. And if you need anything else, just email me. All right. Good to see y'all, and we'll talk another time.